Welcome back. In the previous class, we looked at the concept of pseudo steady state approximation, and we said that it is going to help us reduce the mathematical complexity significantly. Okay. It would reduce the amount of effort that is needed in the mathematics, especially brought on by the partial differential equation, the time variation and the space variation coming in. If we can avoid the effort, we might as well. Okay. And this helps us avoid it. And I was going to illustrate that to you by illustrate better by using this particular problem, which is directly related to our kind of work. Let me read it again for you for completeness. Let us consider the permeability of a model protein albumin through a coating used to improve the cell adherence on surfaces. The permeability can be measured using a cylindrical vessel separated into two chambers A and B by the material whose permeability is being measured. Since the coating is too thin to have the necessary mechanical properties to act as the above mentioned separator between the two chambers, another technique is used to find the needed permeability. The permeability of the membrane with suitable mechanical properties is first measured. Then the permeability of the membrane with the coating of interest is measured. The membrane used in the experiment is circular with an area of 1.33 centimeters squared and the volume of each chamber being 2 centimeters squared, 2 centimeter cubed. The data for the concentration of the albumin, the model protein in B at various times from the start of the experiment is given here, and determine the growth factor permeability of the coating. And you are also asked to assume that the flux through the membrane occurs much faster compared to the change in concentrations on both sides of the membrane. So, let us see how to go about doing this. The solution strategy is going to be something like this. Consider the membrane and the coating to be membranes in series. Okay. You have first the membrane and then you coat a thin layer on it, and it is quite easy to see from your experience that these are membranes in series, their resistances are in series. Thus, their resistances are the inverse of their conductances. The conductance is equivalent to the permeability, right, you know that, are additive. The inverse of the permeabilities are additive. The permeability, as we have already seen when we did the initial steady state diffusion and so on and so forth, is the product of diffusivity and the partition coefficient divided by the length of the membrane or the thickness of the membrane. And the permeabilities need to be found from the given data of concentrations in B at various times. Right. So, this is what it is. To do this, first let us consider the membrane as a system. The strategy is it is continuing. This is the framework, and then we are still with the solution strategy. Let us consider the membrane as a system. If we apply the equation of continuity, A2, C, D, A, B are constants, from 2.3.2-1, I hope you have it handy, please take it and see what it is. We are going to apply this on the membrane. We have chosen the membrane as a system or the separator as a system. So, this is the equation 2.3.2-1 from equation A2 from table 2.3.2-1. Okay. And as usual, we are going to see which of the terms remain. This goes out by the pseudo steady state assumption. It is the membrane that we are considering. Our interest is in the variation of the concentrations in the two solutions, right? And those concentrations vary much slower compared to the diffusion is already given in the problem, and therefore, by pseudo steady state we can write this to be 0. Whether it's actually at steady state or not, it doesn't matter. Also, you know by now that since there is no convective motion of the fluid or there is no bulk fluid motion, the Vx, Vy, Vz, which correspond to the fluid velocities, can be set to 0. Then this is a one dimensional case, we will consider that as x, and therefore, the concentration does not depend on y, therefore, that the derivative is 0. The concentration does not depend on z, the first derivative is 0, and therefore, the second derivative is 0, and of course, there is no reaction that is happening. So, this is the equation that we get for the balance of the species I on the membrane. Okay. This is a big blessing, right? We do not have the partial differential equation anymore. Now, since, well, coming from here, I am going to call dI effective as dm, the diffusivity through the membrane of species I. Dou squared Cm dou x squared Cm is the concentration of species I in the membrane at various x's equal to 0. And since this is equation 2.6-1, since all this is fine, and of course, you know that since x is the only variable here, you can write the partial differential equation as a total differential equation. So, this equation is the same as equation 2.4.1-7 with very similar boundary conditions, and we have already solved this earlier. Okay. You can go back and look at this thing. We considered this when we looked at the steady state diffusion through the membrane a few lectures ago. We have already solved this, so I am not going to solve it earlier. You go back and look, that will be good practice for you to solve it. The concentration profile in the membrane would be Cm at any point x equals Kca minus K of Ca minus Cb times x divided by L, where x is the distance along the membrane from this side to this side. Equation 2.6-2. The flux across the membrane also we had derived earlier was diffusive flux Na equals Ja star, and that we can get from Fick's first law minus dm dCm dx. That was nothing but we have already seen, you can go and see the details of the solution earlier, equals dmk by L Ca minus Cb. So, this is the flux. Equation 2.6-3. Now, let us do a mass balance on the protein over chamber B. Okay, this is a solution strategy. We are still in the solution. How do we actually get the permeability of the coating which does not have enough mechanical properties using the data that we have, which is the variation of the species in the chamber B. So, let us do a mass balance on the protein over chamber B. How do you decide on this? Will come with various, with practice. You do more and more problems, then you see this is going to come out of this, and so on and so forth. There is no easy way of knowing this beforehand, but once you get into it, it is quite straightforward. It's not a big deal at all. So, this is the standard material balance equation. There is no generation of B in the generation of the species in chamber B. There is no output of the species from chamber B. There is no consumption. There is only input through the membrane, and of course, B accumulates in the chamber. So, the input rate of the species needs to equal the transfer rate of the species I through the input rate of the species into the chamber needs to equal the transfer rate of the species through the membrane, because that is the only route inside. And the flux of I through the membrane we know is dmk divided by L Ca minus Cb. And we also know that the rate is area times flux, and we know the area. Therefore, rate is nothing but the area of the membrane, cross sectional area of the membrane, times the same thing, the flux dmk by L Ca minus Cb. We will call this equation 2.6-4. The mass balance of I can be written as dAi dt equals, this is dm dt, right. So, this is the mass of B in, this is the mass of I in B, Cb Vb concentration times the volume dt, and that we got from the previous thing, the rate equals this. So, rate equals AM dm k by L Ca minus Cb, equation 2.6-5. Now, since Vb is a constant, okay, here you can take it out of the derivative. So, you could write this as Vb times dCb dt equals Am dm k by L Ca minus Cb. Or dCb dt, we have just taken the, we have divided both sides by Vb or taken Vb to the other side, Am dm k by Vb times L Ca minus Cb. So, dCb dt can be written from this. You realize that dm k by L is nothing but the permeability of the membrane. Therefore, the right hand side of this becomes Am by Vm times Pm times Ca minus Cb. Now, we have, if we have Ca, the other concentration in the other chamber, in terms of Cb, we can solve this equation. Here we have Ca and Cb, two variables. As Cb changes, Ca needs to change. It is the material in A that is moving to B. So, the concentration in A would change, it will reduce. So, we have two variables here. If we can find the relationship between these two variables, we have solved this particular equation. So, to do that, let us do a mass balance on the protein over the entire vessel containing A, B and the membrane. So, the compartments A, B and the separator, which is the membrane with or without the coating. So, this is the material balance expression. This is the entire vessel, by the way. Therefore, you get there is no input, there is no output, there is no generation, there is no consumption, and the accumulation over the entire thing has to be equal to 0. That is the relationship that we get, kind of an intuitive relationship, but this is a formal way of doing it, so that we are absolutely clear and we have it in a mathematical form that would become useful for the solution. When each compartment and the membrane are explicitly expressed, this is where the usefulness comes. This equation dm dt equals 0, this becomes dVca divided by dt plus dVcb divided by dt plus dVmcm divided by dt equals 0. Okay. See, this is mass rate of change in the chamber A, this is the mass rate of change of the species in chamber B, this is the mass rate of change of species in the membrane. All those three put together must equal 0. The volumes Va and Vb are constant, as well as the membrane are constant. Therefore, they can be taken out of the derivative. Therefore, we get Va dCa dt plus Vb dCb dt plus Vm dCm dt equals 0. And okay, let us call this equation 2.6-6. Now, we have our beautiful pseudo steady state approximation PSSA, and by that the d dt of Cm is 0. It is a steady state, the concentration at any point in the membrane cannot change with time. Therefore, that is 0, and also we know that both A and B have equal volumes. So, Va equals Vb, and therefore, this equation becomes, this thing goes away, Va and Vb get cancelled out because they are equal. Therefore, d dt of Ca equals minus d dt of Cb. Okay, just take it to the other side. Equation 2.6-7. The initial condition, that is at t equals 0, is Ca equals C0. The entire albumin or the model protein is in chamber A. Equation 2.6-8 and Cb equals 0. Equation 2.6-9. This is what happens at t equals 0. Okay. So, now if we use this and solve the differential equation here, we will get Ca equals Co or C0 minus Cb. Okay. Straightforward, I'll let you solve that. That's a very straightforward thing. It's good practice for you. We'll call this equation 2.6-10. If we substitute this in if we substitute this equation in 2.6-5, what is 2.6-5? It is this. Okay, this written in terms of permeability and so on and so forth. Okay, we can consider this as 2.6-5. Yeah, this is what it is. Ca was C naught minus Cb, therefore, we substitute C naught minus Cb minus Cb, so C naught minus 2 Cb. The rest are Am, Dm, K by L, and on the right hand side we have Vb, Cb, dCb, dt. Okay. So, we have this in terms of the only variable Cb, and so you can solve it. For that, let us number this as 2.6-11. Now, if we integrate 2.6-11 with the initial conditions Cb equals 0, then we could get the solution. And for integration, note that this equation is of the standard form, okay, dx dCb divided by a plus bx, because this would come down to the other side, C naught minus 2 Cb, a plus bx, a is C naught, b is minus 2. Okay. So, the solution of this is nothing but 1 by b ln of a plus bx. This you know from standard mathematical tables, integral tables, and therefore, the solution becomes minus 2am dmk by vbl. Okay, the solution of this differential equation. This is the vbl times t equals ln of C naught minus 2 Cb by C naught. Okay. This is what comes about. One, you could probably write down the steps and check. This is the integral of the equation. You take this to the other side, Vb comes here, you could dt comes here, and this is the solution. Okay. Why don't you write it down and check? You will be able to figure that out. We will call the solution as 2.6-12. Okay. Now, look at this form. Okay. What do we have? We have concentration variation in B as a function of time. Okay. So, that is what we have here. We have Cb and T. Okay. So, this is of the form that we can directly manipulate with the given data to get the permeability dmk by L. Okay. So, that is what we have come down to. So, let me show this and then just quickly review. So, a plot of y equals m times x. So, a plot of y ln of C naught minus 2 Cb by C naught versus x time will provide this as the slope. M is minus 2 am dmk by vbl, dmk by vbl, dmk by L is nothing but the permeability, and therefore, from this you can get the permeability. So, Pm equals dmk by Lm, equation 2.6-13, and our solution strategy was the membrane and the coated layer act in series for the transport of the growth factor when both are present. Thus, their resistances or the inverse permeability values were additive, and therefore, 1 by Pt total equals 1 by Pm plus 1 by P of the coating layer. That is what Cl stands for, the coating layer, and we are interested in the permeability of the coating layer, and therefore, if we use the first set of data with the membrane alone and plot ln of C naught minus 2 Cb by C naught versus T, from the slope we will get Pm, and then when we use the data with the membrane plus coating, we would get P total or Pt, and from these two we can get P of the coating layer. Okay. So, this is the strategy here. Let me quickly tell you what we did on an overall basis. We just used material balances and so on and so forth in a fashion that will give us a solution. We had first considered the membrane as a system, wrote the balance, the equation of continuity, and got some useful expressions for what happens in the membrane. And then we did a mass balance on the protein over the chamber B alone, and then we did a balance on the overall chamber, that was overall chamber, and we got useful expressions for our particular situation. And we found that if we plot ln of C naught minus 2 Cb by C naught versus time, this will give us a slope which contains the permeability, and therefore we can back out the permeability from this. And by using the two sets of data separately, we would first get the permeability of the membrane from the slope of the line that we just mentioned, and then the second set of data would give us P total, and from those two data values we could the slope values and therefore the permeability values, we can back out the coating layer permeability. Let me do one thing. Why don't you stop here, go through the solution, use a spreadsheet or a graph sheet or something like that, do this problem. Okay, actually work out the various numbers there, plot and get the slopes, and that would be a very good learning. I have given you the solution because it is not very straightforward, and therefore I thought I'd give you the entire solution. But let me, I'll ask you to stop the video here, go back and do that whatever time it takes. It might take half an hour, 1 hour, whatever it is, and then come back and check your values. Please go ahead and do that. Only if you do that will you really learn. Otherwise it is just looking through a set of video, the learning set of lectures. The learning will not be appropriate. Learning is what you give yourself. Okay, this is just information to guide you into you learning for your own. The learning is always done by you. Okay, I can only show you the way. Go ahead, please. Pause. Okay, hopefully you did that. You could check your values. The permeability of the membrane, hopefully around this should be fine. There would be slight variation in your graphs and so on and so forth. That doesn't matter. 4.8 into 10 power minus 5 centimeter per second. The total permeability is 1.1 into 10 power minus 6 centimeter per second. And therefore, the permeability of the coating layer is 1.12 into 10 power minus 6 centimeter per second. Okay. Almost the entire resistance for the growth factor flux in the evaluation system is provided by the coating. Why? Because the total permeability is 10 power minus 6. The membrane permeability, it allows everything to pass through 10 power minus 5, an order of magnitude less, almost half an order of magnitude less, and the coating layer is 10 power minus 6. Therefore, this is the one that is providing the biggest resistance or less transport in this case, and the entire resistance to the growth factor flux is residing in the coating layer. Okay, that's it for this class. When we begin in the next class, I will summarize what we have done in this chapter. Okay, that completes the chapter on mass flux. I will summarize what we have done in this chapter and then move on. See you then.